This is the first part of 2 videos covering IPv6 concepts. We will discuss writing and reducing 128-bit addresses, prefix length concepts, and the 2 types of addressing, private and public. The size of an address in IPv6 is 128 bits, which is 4 times larger than an IPv4 address. An IPv4 address is a 32-bit address, permitting an address space of over 4 billion possible IP addresses. IPv6 uses a 128-bit address space and permits an address space of 2 to the power of 128 addresses. This equates to more than 655 sextillion addresses for every square meter of the Earth's surface. Because IPv6 addresses are so large, they are typically represented in hexadecimal format instead of the decimal notation typically used to represent IPv4 addresses. IPv6 addresses are broken down into 8 groups of 4 digits or 16 bits separated by colons. Here are a few examples of typical valid IPv4 addresses that illustrate this IPv6's naming scheme. Because IPv6 addresses are so long, the IPv6 standard provides a few simple rules for simplifying their notation. 2 of these rules are discussed here, including name of : rule, name of leading 0 rule. The first rule uses a double colon to represent a group of multiple groups with consecutive 0 values in an IPv6 address. It bears repeating that this rule only applies to groups that consist entirely of zeros. Groups like 0001 cannot be shortened by this rule. This rule can only be used once per address. Each node or device can expand the value by calculating the number of bits missing and replacing them with zeros. Let's look at how our new rule applies to our previous set of IPv6 addresses. The second rule allows the leading zeros in each IPv6 group to be omitted. For example, a group consisting of 0001 could be reduced to 1. Unlike the first rule, this second rule allows us to simplify individual groups like 0001. Let's apply this second rule to our already simplified addresses and see how they become even more simplified. IPv6 is similar to how IPv4 uses the prefix length in the subnet mask to determine network and subnet. An IPv6 prefix length is written as a slash followed by a decimal number. The prefix length, which will be an integer between 1 and 128, illustrates how many bits of the IPv6 address define the network and subnet. Here is an example of an IPv6 address including a prefix length. The network prefix shown is indicated by /64. This prefix includes an encoding of its 48-bit IPv6 global routing number, an encoding of its 16-bit internal subnet ID, and an encoding of its 64-bit interface identifier. /64 prefix lengths are by far the most common. However, you should still be able to manage IP addresses using a prefix length that is different. In particular, when using a prefix length that happens to be a multiple of 4, you do not have to think in terms of bits. You can think in terms of hex digits. This means that you can take the prefix number, divide it by 4, and subsequently use that number to help identify your network address. Consider the following address. 56 divided by 4 is 14. Moving from left to right, you count over 14 hex positions, and the rest of the hex digits will be 0. Resulting in the following network address. Here are a few examples to practice on. With IPv6, LAN traffic can be one of 3 types: UNICAST, MULTICAST, and ANYCAST. As illustrated, UNICAST, or one-to-one traffic, describes a scenario where data is transmitted from one LAN host to another single LAN interface. As a simplification, unicast traffic can be thought of as traffic directed from one device directly to another device. Multicast, one-to-many traffic, transmits data to a subnet of all devices that are the recipients. As shown in the illustration, multicast traffic is transmitted from a host to all devices on a network, and a subset of hosts listen for the multicast data. While all devices hear multicast transmitted frames, all the devices not currently listening for the multicast data ignore the transmission. If you are familiar with the broadcast traffic of IPv4, multicast can be thought of as the IPv6 equivalent. IPv6 does not support broadcast traffic, so multicast essentially replaces its functionality. ANYCAST, one to nearest, defines another standard for transmitting data to multiple devices that is unique to IPv6. Unlike multicast, it has no direct analog in IPv4. ANYCAST address defines a group of computers with addresses that have the same prefix. Conceptually, an ANYCAST message is equivalent to a multicast message, but the message sent only to the group of computers defined by the ANYCAST address. When routing an ANYCAST message, the network decides which location to route a user request to, based on routing protocol cost and possibly the health of the advertising server. This is an easy way to provide load balancing and redundancy in networks. Common uses of ANYCAST include DNS server load balancing networks. The concrete addressing and dynamic routing make IPv6 ANYCAST traffic more secure than IPv4 broadcast traffic. Note that IPv6 allows multiple addresses to be allocated per interface. There is no concept of primary and secondary IP addressing in IPv6. Unique local addresses, ULA, replace IPv4 site local address scope, which were depreciated for IPv6. They work similar to the private IPv4 addresses, since they do not route on the public IPv6 internet. Therefore, you can use them when you only want to communicate within your own network. This is particularly useful for highly secure private networks, such as those used in research labs, military facilities, or power plants. The network engineer can create ULAs without any registration or assignment process. The first two hex digits must be FD. This is followed by a 40-bit unique identifier, which is randomly chosen. Bits 48 through 63 define a 16-bit subnet identifier. The last 64 bits define an interface ID for the host portion. Global unicast addresses are used for generic IPv6 traffic. These are the same as the public addresses used in IPv4. IPv6 addresses are made up of three parts: a 48-bit global routing prefix, provided by the Internet Service Provider, a 16-bit site prefix, or site topology, and a 64-bit host portion. The global routing prefix is unique for each company and can be compared to the different classes of an IPv4 address. Originally, IANA reserved addresses that begin with a hex 2 or 3 as global unicast addresses. However, they have since broadened the scope except for the few allocated for other purposes. Unique local addresses use the FD, multicast uses FF, and the link local uses FE80. A company can then subdivide the large address block into subnets. Subnetting IPv6 is similar to subnetting in IPv4. Similar to IPv4, each VLAN and for each point-to-point WAN connection still needs a separate subnet. The interface ID must be unique within a subnet. IPv6 hosts can use the Neighbor Discovery Protocol to automatically generate their own interface based on the MAC or EUI64 address of the host interface. You can also manually assign the interface ID. Manually configured interface IDs are recommended for routers and servers enabled for IPv6. Alternately, addresses, default router, and DNS settings can be learned using a DHCP server. Here are the answers to finding the IPv6 prefix. Here are a few examples to practice on. In conclusion, we discussed how to interpret an IPv6 address and demonstrated how to reduce the IP address to make it shorter and easier to read. Further, we discussed the difference between unicast, multicast, and ANYCAST. Finally, we presented the difference between global and private IP addresses.